Welcome back to the series, everyone. In this episode, we are going to be troubleshooting the newly rebuilt power supply. So before we start, I need to give you a very brief and easy overview of this very simple power supply circuit. So here are the schematics for the power supply unit. These were produced by the Dynamic Personal Computer Users Club, which is a club from back in the day, when the DAI was being sold in the early 80s, late 70s. I found that there are some differences between the values that you're seeing here and what I had in my machine. For instance, this resistor here going to the comp pin of the switching regulator. In my machine, I believe this was 33K. Or is 33K. And this resistor here, which goes from the base of the first transistor in the Darlington pair to the base of the next one, the big pass transistor, which is a tip 34. In my machine, this is 1K instead of 100 ohm. I believe it will work either way, but there are some differences. I don't know how reliable this is, but I will be assuming it is reliable. The way this works is very simple. We have an input here, which today is 230 volts, no longer 220. That's the power switch. And then there is a transformer. The primary, there are actually two primaries in the transformer I have in my machine, but they are connected together to form one 230 volt primary. The secondaries are also connected together and tapped at ground in the center. And so instead of having a large amplitude sinusoidal wave, you get a much lower amplitude here, but still AC. And then that goes into this bridge rectifier. So at this point here, pretend for a moment you don't have this bulk capacitor. At this point here, you would have this, a rectified signal. So let's say this is time, T, and this is voltage, V. So here, on this point here, you would have only the positive cycle of the sinusoid. And then here, you would have the mirror image of it. But because there is this bulk capacitor here, we would get, instead of this pulsating signal, we will have a little wavy signal at the required voltage. And then there is one more filter cap here to filter out some high voltage jitter that you may have on this curve. The main part of this power supply is this Darlington pair here. This is the pass transistor. Let me try to explain this without detail, so at a glance, so you understand this. This is the switching regulator, and what this does, it will switch the Darlington pair on and off depending on this signal here, which is the feedback. This is actually not VREF. This is wrong. This is not the reference voltage. This is the 5 volt rail. Which is spied on here and goes back into this chip. If the voltage here is higher than the 5 volts that it's supposed to have, then through these two pins here, pins 12 and 13, there will be no base potential applied to the first transistor of the pair, and therefore there will be no base potential to the pass transistor, and therefore there will be no current going through between emitter and collector of the main pass transistor. It will be switched off, and then this potential here will climb down. The moment let's suppose 5 volts is here. When it goes below 5 volts, this signal here will tell the regulator, okay, now it's below 5 volts, so potential is applied here on the base of the first transistor of the Darlington pair. So a current flows between emitter and collector, but this applies a potential on the base of the pass transistor, and a much larger current will pass this way, building up the potential, so it will climb, and so on and so forth. And the idea is that over time, this will stay around 5 with some switching noise, some jitter, some ripples. That's the idea of this. This is the flyback diode. These days people call it by a different name. I have heard things like a catch diode. I have heard recovery diode. This is a flyback diode, and it's important because of this large inductor here, which is supposed to stabilize the signal. But inductors, they resist changes in the current that is passing through them. When current is passing them, energy builds up in the electromagnetic field that circulates around them. You have these field lines going around the inductor, and they build up energy. When this transistor here is closed and current is passing this way to the 5-volt rail. But when the switching regulator opens this transistor, so there is no current passing through it anymore, and there was current passing through the inductor before. Now there is none, because this is basically an open circuit here, this transistor, the pass transistor, it's not passing anything. The inductor will resist this decrease in the current. It will take energy from the electromagnetic field that has built up around it and convert it into an electric potential to try to maintain the current. And to do that, normally this is biased this way, positive and negative, so current flows this way. But when current is interrupted and it's no longer passing through, the electromagnetic field around it will begin to collapse, and as it collapses, it will build up an opposite potential here, minus and plus. So this will remain what it was before, but the potential here will go down, and the idea is if it's plus here, this will be going down a lot in order to try to force current through this open switch, this open pass transistor, to maintain the current through the inductor. That's the idea. The problem is that this negative potential that will build here, it can be 10 times higher than the normal operating voltage. So if you're talking about 5 volts, this can go to 50 volts, even 60 volts here. And if you don't have this diode here, so that current can flow from ground into the inductor, because this is now a negative potential, it's more negative than ground, so current will flow from ground into the inductor in order to maintain the current through the inductor and convert the energy in the electromagnetic field into current. If this diode is not there, then this current will have to come from here, and this negative electric potential of 60 volts will be applied here and therefore here, and it will blow these transistors. Actually, it will probably blow this one. This is a very robust pass transistor, can pass a lot of current, can survive very large potentials like 70 volts. Even I plan to put a tip, but instead of a tip 34, which is no longer manufactured, I plan to put in there a tip 2955, which is just like the 34, but it stands even higher voltage. I think it stands even 70 volts. So this will not blow, but this will if you don't have this flyback diode in here. So basically what happens is when the pass transistor is closed, current flows this way. When the pass transistor is open, then current flows this way. And they will be switching between one and the other in such a way as to maintain the potential at around 5 volts. That's essentially how this whole thing works. And then you have some more filter caps here, 100 nanofarads for the higher frequencies, and a 4700 micro for the low decoupling frequencies. And this line here, which basically provides the feedback, forget this VREF, it provides the feedback. There's a voltage divider here. You see 2 identical resistors. So the voltage potential here will be half of that. And you might ask, why? Why only half? It's because this thing will compare voltage reference to what comes into through this pin. And it's much easier to build it with a lower voltage reference, like 2.5 volts instead of 5. So we put a voltage reference of 2.5, and then we divide this voltage here through this voltage divider to identical resistors. So the point, this will be here at 2.5 volts when this is at 5. So it can be compared to a voltage reference of 2.5 volts as well. So that's the idea, and then some more filter caps in there. This is not on my board. It has not been populated, probably not needed anyway. Here, this pin 9 is the comp pin. This is basically the input for an error amplifier. You just basically amplify the error you're trying to correct for to keep this voltage stable. There is some more biasing stuff going around. So essentially, that's the circuit for the 5-volt line. What I found very striking and concerning was that these 4 pins here are grounded. And these 4 pins, 4, 5, 11, and 14, they are used for current limiting. So we are supposed to put some discretes connected to them in order to limit the current at a level that we select by choosing these discrete components in the correct way. The fact that they are all grounded means that there is no current limiting feature anymore. So the current limit for this circuit is basically this fuse. It will either blow or not. There will be no intelligent, active current limiting control, which it should be there, you know. The functionality is built into this part, the SG3524 switching controller. So why didn't they do that? And it really should be there. So that's a bit concerning. Okay, this whole thing is about the 5-volt rail. There are 2 other rails. There is a 12-volt rail, which is controlled by a linear voltage regulator. This is the 7812. And then there is a -5-volt rail where the memories and the CPU, the 8080, require these 2 extra voltage rails. This is regulated by another linear voltage regulator. That's the 7905, which is the negative version of the 7805. There is a little decoupling cap here, another decoupling cap there for the higher frequencies, and one here for the higher frequencies as well. So that's essentially it. This is an extremely simple power supply circuit with 2 linearly regulated rails and 1 switch mode rail. It is simple to the point of almost being irresponsible, especially because there is no current limiting in there, and the filter cap, the bulk capacitor here, is fairly small. I would expect to see, in the SOL 20, this is a 22,000 microfarad, 22 millifarad cap. This is 4.7 millifarad. This one here, it's large because it's already on the 5-volt rail, and because the current limiting feature is not being used, the inrush current into this cap can be dangerous. That's probably not an issue because this coil here will resist sudden changes in current. But still, you have an inrush current in here, and there is no current limitation in this circuit. And this whole thing happens before the fuse. So yeah, I'm not a fond of this power supply circuit. I think DAI was excellent as far as computer design is concerned, digital design. But when I look at this, the thought that comes to my mind is they didn't have a power supply engineer in their staff. They probably just copied it from reference designs in data sheets. And they probably didn't know very well what they were doing, because this is simple to the point of being irresponsible. I am going to put TVS diodes on these rails, or at least I plan to add at least 1 extra layer of protection. I even considered actually populating these pins, but this is a very rare machine that's going to go to a museum, and I don't want to butcher the board. I don't want to disfigure the board by adding a little subboard bodged into the main power supply. It will look horrible. and it will not be the original die. So yeah, let's see how this will proceed. So here we go, the first full integration test. I'm putting the little daughter boards back in the system. At this point I'm still naive, thinking that everything might just work. So I'm putting everything in there. The next board is the video card. There are 3 possible video cards for the die. One is RGB, the other one is all color, and another one is black and white for monochrome monitors. This is the one I have, I'm afraid. So we'll get black and white video. There are options to get color back. I will discuss it in a later episode. For now, I'm just connecting everything. I'm going to turn it on. I have safety glasses on because I expect some of those tantalum capacitors to blow. There is no image on the screen. I'm using the RF modulator. I still would have to tune it. But before I even get there, I start feeling a funny smell, a smell of burning. So, okay, that's reason enough to stop everything I'm doing and check. But I couldn't identify the source. So the next thing to do is to check the voltage on the 5-volt rails, to see whether we have a short. And look, the voltage is at 2 instead of 5. We seem to have a short somewhere, a short under voltage. So I take a thermal camera and I turn the machine on with trepidation. I don't like to do this. Knowing there is something wrong, I still turn it on, but I need a clue. I need to know where to begin. And if something is shorting out, it will get hot and it will be visible on the thermal camera. But the only thing hot is the pass transistor. The rest of the entire board is pretty cool. So the problem seems to be inside the power supply unit. Not in a chip, not in a diode that is shorting out under voltage. It seems to be in the PSU itself. So I turn my attention to the PSU itself, and to isolate it, I remove the little fuse that connects to the 5-volt power rail. And then I discovered that there are 2 jumpers, you see them there. They connect the other 2 power rails to the motherboard, the 12-volt and the -5-volt. So if I remove those 2, and I did, now the power supply is electrically isolated from anything else, and I can turn my attention exclusively to it. Now, the first test is to check the impedance to ground of all the 3 power rails in case there is a passive short. There is a blob of solder somewhere. And no, the impedance without voltage is pretty high on all 3 power rails. So the short is something related to applying voltage. It's like a diode. If you apply no voltage, it's not a short to ground. But if you put voltage on it, it's very close to a short to ground. So the problem we are seeing here is of that sort. It only manifests when we put power in the circuit. And since the circuit is the PSU itself, I will turn it on again, isolate it from the rest of the motherboard. And I'll check for the voltage level again. And there we go. There is very little there, 0.3, 0.4. So yeah, we have a problem in the power supply unit. Since I've removed this fuse here, we know there is no current flowing that way. And we still have the problem, we still have the low voltage on this rail. So this is not a short circuit or leakage somewhere on the board, because this fuse is not there. And the power supply is isolated, so there is a cut in here. So whatever current is leaking to, preventing 5-volt potential from building on this rail, it has to be here. And if you look at it, there is an obvious place where it could be leaking. It's through the flyback diode. If this diode is leaking, if at only a few volts potential, it's breaking down and allowing a current to flow this way, which a diode should not. This diode should only allow current to flow this way. But if it has failed, and this is a failure mode that we may not detect with a multimeter, because the multimeter applies a relatively low voltage potential here, and if no current flows this way with that voltage potential, multimeter will say it's okay. But if this is oscillating above 5 volts, maybe that's enough for current to flow this way if this diode has failed. I don't see another, but there is no other place where this could be happening. This capacitor is okay. I had a look at it. There is no short through it. This capacitor is brand new. I know it's okay. So it's got to be the diode. It's got to be this diode. So I'm going to replace this diode with another one I have. I cannot install it properly on the can of the power supply, on the shielding, because mine is such that the stud, this diode usually has a form like this. Seen from the side, it's like this, then the wire comes this way, and then here there is it's basically a bolt-like protrusion, and you can put a nut like this. In my case, the diode is like this. So the stud, which is this part here, is on the wrong side. So I can't install it in the can. So you're not going to see it. I'm going to bodge it underneath. I'm going to put a replacement diode in there. We cannot operate the machine without this diode. I think I explained it before. This diode allows for current to flow this way when this transistor opens up this line, and the magnetic field around the inductor collapses and builds a large potential here. When it does that, current has to come this way, because otherwise that potential will build up on the two transistors of the Darling pair, and it will destroy them. Well, certainly this one will be destroyed because it's a small one. So we cannot operate this without this diode, and I don't have a direct replacement right now, so I'm going to bodge an alternative, and let's see what happens. So here I go. I will pull out that diode, the flyback diode. It's bolted to the shield. With a little torque wrench, I managed to get it out, and then I bodge in a new one in underneath, and test it, make sure everything's okay. And let's run it again. I remove my grounding strap because I don't want to get electrocuted. I have my thermal camera ready to see whether anything still gets hot without that diode. And lo and behold, the pass transistor doesn't get hot at all. It's cold. And for a moment I thought, oh, this may have solved the problem. Look at that. The pass transistor is completely cold. What you see a little bit hot is a 12-volt linear regulator. So I thought, well, maybe we solved the problem, but it's cold because there is no load and it's working. But unfortunately, that's not the case. And so I turned it on again and tested the voltage on the 5-volt rail. I was measuring resistance. And let's measure voltage now with the thing on. I should see 5 volts if it's okay, but still 0.39, 0.4. No, still have a defect. So I stick with my theory. I think one of the transistors in the Darlington pair has blown, and I bet it's the BD140 because it's the fragile one. I already desoldered it, but the pins were bent, so I have to use a plier to pull it out. There he is, a fragile BD140. So let's test it, and I was quite sure it would be busted, and it is. You see, there is an open there. The tester says the leads are connected together. So there is a bare short. But this doesn't explain the problem. We still have a mystery that we have to investigate. All right, so I changed this diode here, the flyback diode, which I thought is the only path to ground. And I know for a fact that after I changed it, the Darlington pair was still working. This transistor was not yet busted. But now it got busted. And this is exactly what I would expect if indeed there is current still flowing to ground here, because the BD2955, which I replaced for the TIP34, it's a much more robust transistor. The BD140, which is connected to the same collector, which is this point here, it's much less robust. So by changing this diode, apparently I didn't solve the problem, because there clearly is still something leaking to ground, which caused this transistor here to get busted. And we know it's busted now, and I knew it was not busted immediately after I changed the diode because I checked it. So what's going on? The only path to ground is through this diode, and now it's a good diode, I know for a fact, and there is no other path to ground. Or is there? Is this the only diode? Of course it's not, because I am an idiot. I'm a bloody idiot. I put, remember, a TVS diode, not this way. I put a TVS diode in here, also going to ground. And I make no, this is the first mistake. I'm thinking in terms of there being only this diode, while there in fact are two, because I put the second one. And the other mistake, which is even much more stupid, I put the TVS diode before the fuse, which is not where TVS diodes are supposed to be. They are supposed to cause the fuse to blow as opposed to the circuit to blow. So the way to do it would have been to put the TVS diode here. So when the voltage goes too high over here, a lot of current flows down to ground and blows this circuit, therefore protecting whatever is in here hanging from the 5-volt rail. So two mistakes. The first one, a rookie, stupid mistake in my attempt to put the TVS diodes with as short leads as possible in an as inconspicuous way as possible. I forgot about the fuse and I hung it before the fuse. That's the first mistake. And the second mistake is forgetting that I have done this and thinking that this is the only problem. So obviously the TVS diode is being a problem, which now raises some other questions. And the reason is the TVS diode has a breakdown current of 6.3 volts. In other words, it only really starts conducting significant current this way when the potential here is above 6.3 volts. Now, through this feedback loop that we've discussed before, the switching controller, the SG3524, is supposed to keep the ripple here well below 6.3 volts. Now, yes, this diode will start conducting a little bit of current before the official breakdown voltage. So when it goes a bit above 5, some current will start trickling here. At 6.3, it will be more significant. And at around 9, I think it will clamp. It will clamp down. Everything will flow this way. Nothing will flow that way anymore. That's the way it's supposed to work. So allowing for that, let's say that, even before 6.3 volts, current starts trickling down. But even then, this shouldn't happen. It will only happen if the ripple here is so large, something like this. And let's say at this level here, you have your 5 volts. At this level, well, this is actually time. But let's say that this is 5 volts. So we have voltage here, time is in here. So forget this. So this is the 5-volt level. Now, if there's a lot of rippling, and this rippling is going, say, to 6.5 volts, somewhere here, then that will trigger a breakdown of the TVS diode, and then current will flow to ground and bust this transistor. And now the question is, what is the ripple in there? So the way to go about it now is to, first of all, take the TVS diode that is in here and eliminate it, take it off the circuit, and then, of course, I have already replaced the BD104, the brand new one, manufactured last year. So without the TVS diode, this should be able to operate long enough for us to measure a few things, including the voltage potential on this point, and look at it in the oscilloscope and measure the ripple, see what's happening. That's the way to go forward now. So with the new BD140 in place, let's check the voltage isolated from the rest of the computer, and we get our 5 volts. It seems to be working now without the TVS diode and with the new BD140. I test it again, it's indeed 5 volts. I looked at the ripple, and now I have to take this with a grain of salt because it's unloaded. I'm not connecting the power supply to the rest of the circuit yet, but there is very little ripple, well below 50 millivolts peak to peak. So the power supply seems to be working okay. I'm measuring it right at the input of the fuse, but it's unloaded. So it's easy to operate okay if you're not trying to compensate for the current consumption of the computer proper. So let's do a more complete test. I connect it to power once again. Now I have my television connected to the output of the RF modulator in case we see something now that it's working. The oscilloscope is connected to what I believe to be the composite signal coming out of that little board, which I think is a composite mod. I reconnected the power supply to the rest of the computer, those 2 power rails there, plus the fuse for the 5-volt rail. And now we can, for the first time, try to run this thing with the power supply apparently operating and see if we get anything on the screen, or at least something on the oscilloscope, which would be the composite signal. I'm eager to figure out whether there is still life in the digital part of this computer. And I'm holding my breath now. But there is nothing to do but to try. So I put my safety goggles on in case those little tantalum capacitors blow on my face. I reconnect the computer to the power socket. My thermal camera is at the ready in case something is getting too hot. Of course, the TV will not show anything at first because it's not tuned in, but I want to make sure that there is nothing super hot. And now I try to tune in to an image, but it will be futile. The oscilloscope, however, shows a well-formed composite signal. Let me show it to you closer. It's a well-formed, clear composite signal coming out of this little red wire from the mod board. It's jittery, it's obviously jittery, and it doesn't have a color burst. The back port is flat, it doesn't have a color burst. So this is indeed a black and white video card. But we do have a composite signal, even though my TV is not tuning in to the RF signal. I tried it manually, I tried it automatically. I see that there is an image there sometimes, but it doesn't manage to really sync to it. And I keep obsessively monitoring the temperature, especially of the pass transistor. It is high, but it's usual high. It's not above 60 degrees Celsius. It's under 50 or 50 something. So yeah, I want to see whether the computer is alive, so I make this composite mod the way it should have been done. Instead of an extra RCA connector, I bring the composite signal to the RCA connector of the RF modulator using a twisted pair. One of the wires is ground connected to the CAN. It's really soldered to the CAN. It's to prevent interference. And the little resistor that would pass the modulated signal to the RCA plug, I moved it away. So now there's composite coming out of there. This twisted pair thing, it may not work much. It helps with interference, but I should have done it with that other little red wire, because that's the one that will be picking up interference right now. I'll do it later. At this point, I just wanted to see whether there is life. So I will redo the test, but this time the oscilloscope will be connected to the 5-volt rail, because as per our original plan, I need to check the jitter, because the rippling, because I think the rippling was the source of our problems. So let's check the rippling now. Holding my breath, turn it on. There we go. The television will take a while to lock into the composite signal, and I have to adjust the parameters of the oscilloscope so I can see something proper on the screen. But in the back of my mind is always the temperature. Is the temperature okay? And there's the ripple. And it's massive. It's gymongous. And the TV is still not managing to lock in. And oh, finally it logged in. There is a proper starting screen there. It's jittery, but it says DAI Personal Computer. I will show it to you in a close-up shortly. But I want to make sure that nothing's too hot. I'm paranoid about that part. And here's a close-up of the ripple on the 5-volt line. This is not normal. Every division is 100 milliamps. So we have almost 600 milliamps ripple peak to peak. That's completely unacceptable. It's not only bad design, the computer cannot survive this for long. And here's the image, DAI Personal Computer. The computer is alive. The digital part is alive. The video signal is horrible at the same frequency, about 50 hertz, as the rippling. So I think the distortions on the video image are because of the rippling of the 5-volt rail. These are not two different problems. It's one and the same problem. I decided to quickly type in a program, the usual 10 print and 20 go to 10, to see if the processor is executing a user code, and it is. Look at that. Hello from Belgium, the birthplace of this computer. And if you look at those waves on the screen, you will see that the frequency matches the beat interference on the oscilloscope, which is the 5-volt rail rippling. Now I have a strong suspicion what is wrong. But before we can investigate further and do some more tests, I need to stabilize this machine as far as temperature is concerned. I was doing this on a very hot day. It has been very hot in Northern Europe. We are not used to this. So the thermal imaging has shown that there are 3 ICs on this board, one DIP 14 and 2 DIP 40 chips, including the CPU. They get hotter, significantly hotter than the rest. At over 60 Celsius. So I put heat sinks on them using thermal glue. And then I have to have patience because the thermal glue takes a few hours to completely dry. So I cannot do anything, but I need to give this machine a rest, especially because it was a very hot day. This was yesterday, and it was a pretty hot day for our usual Northern European summers. But I need to feel that the machine is stabilized, that I will not ruin it by running it. I put a little fan, a USB fan, trained directly at the pass transistor, and I connected the oscilloscope to the bulk capacitor just at the output of the bridge rectifier. And look at that. 2 things are important here. The peak is at 15 volts instead of 22. And it's oscillating at 50 hertz, which means that there is not enough input voltage to the bulk filter capacitor to produce a DC signal. That's the problem. I am not getting enough voltage out of the secondary of the transformer. It's probably the wrong transformer. I decided to check further. That's the minus 5-volt rail. Now the 12-volt rail will tell us what we need to do. We need to know to confirm, and look at that. Beat interference at 50 hertz. It's not getting enough input voltage to regulate the output at 12 volts. And that's typical of the output of the transformer not being high enough. It doesn't charge the bulk capacitor enough for the capacitor to not discharge too much before the next pulse comes in. And here we go, another embarrassing moment for your watching pleasure. I made a fool of myself again. As you know, the primary winding of the original transformer was open, so I needed to get a new transformer. And the original transformer did have a label, but it didn't tell me what the voltage swing was of the secondaries, what the maximum current capacity was. It only told me, I think, the voltage in which it was tested, which is a very high number. But it didn't give me specs for me to figure out exactly what transformer I needed. So I looked at these values here provided by the Dynamic Computer Club. It gives you for each power rail a maximum current specification. This is, I mean, in operation it will be a lot less than this. This is for a fully populated board without peripherals and plus some sandbagging. And I calculated that between 50 and 60 volt amperes power would be safe. And it turned out that this fits with the dimensions as well, so I was pretty confident about this. What I needed now was the voltage swing peak to peak of the secondaries, because that's what determines the trade-off between volt and amp at the output of the secondary. Do you get a high voltage and low amps, or do you get high amps at low voltage? And I had this number that I saw in these schematics. I have been looking at these schematics for the past few days, and these numbers stuck in my head, plus 22 and minus 22. And it so happened that I had a couple of toroidal transformers at home, and one of them had a peak-to-peak voltage swing on the secondary of 24 volts. And in my mind, 24, that's close to 22, that's the transformer I needed. And that's what I put in the machine. That was pure wishful thinking. I had the transformer, so hey, it happens to have the right dimensions and the right specs. But of course, this is completely wrong. The plus 22 volts here is the rectified output of the bridge rectifier already filtered by the bulk capacitor. So if we have voltage over time plot, so this is voltage and this is time, what this means is that the voltage will oscillate around a value here that is 22 volts. So it's DC. That's what this means. This is DC. It's not the AC voltage swing at the output of the rectifier. If we ignore for a moment this bulk capacitor, if we just look at the output of the secondary and already rectified by the bridge rectifier, what we will get is this, a pulsating DC signal, rectified. And after you add the bulk capacitor, you get from this, you get this. But let's ignore this for the moment. Consider only this. The transformer I'm using means that the peak value here is 24 volts, not the DC value that you get here. How do you go from here to here? How do you do that? Well, there is a simple formula. You get the peak, so your DC value will be the voltage peak times 2 divided by pi. But I ignored this. I just took the voltage peak. And if you do that, then from 24 volts, you get like 15 volts DC here or here instead of 22. To get 22, you need a peak voltage of about 36 volts, peak to peak. That's the AC voltage swing that you need to get the 22. And instead of that, I'm giving it only 24, and that's the problem. That adds a lot of jitter here on the input signal. And then the switching controller will try to compensate for that on the output here. Now, this does explain the low frequency envelope of those oscillations that you see there, that the beat interference modulating the envelope, but the high frequency switching within the envelope, that's another problem. The wrong valued transformer doesn't explain that. So there is still stuff to do. We still have to investigate this better and try to figure out what is the source of the high frequency oscillation. The low frequency one, the envelope modulation, I'm pretty confident that will be solved once I put a new transformer there, properly specified transformer that I've ordered. It will arrive in 2 days. And then we have to continue this exploration. So stay tuned. There's a lot more to come still. Thanks for watching, and I'll see you next time.